Our next student is Mike Hopkins, who is studying physics. His thesis is titled Mapping Molecules with Infrared in the Near Field. Mike.
Hello, I'm Mike, and I'm a microscopist. The goal of microscopists was once one of reductionism, to see the very smallest and to build up from there to understand the whole. Now, since the advent of the electron microscope, and recently the high-resolution electron microscope, we can see all the way down to atoms. And quite honestly, we're not going to see too much farther than that without a lot of work. So the goal of microscopy has changed. Now we use more of a systems approach. Now the systems approach is taking these small atoms as they bind together to form molecules, and really what we want to see is how these molecules interact with themselves and with their environment. We have two main ways that we do this. One being the electron microscopy, two being fluorescence tagging microscopy. Now the downfall of both of these, though they are both great methods, is that they affect either the sample itself or they affect the environment that the sample is in. So you don't get a true reading. There's a third method, which is spectroscopy. Now, spectroscopy uses the inherent fact that molecular bonds will absorb characteristic photons, so photons of a certain color, and they will convert that energy into motion. So essentially, you can start making these molecules dance by putting in the correct wavelength of light or color. What I try and do, well, let me tell you a little bit more about the spectroscopy. I've got a second here. And that is that spectroscopy will work out in such a way to where you can make molecules, say, stretch. You can make molecules wag. You can make them sway and rock. All of these different dances can be produced. But with spectroscopy, we currently have about 1 millimeter spot sizes. That is, you illuminate about 1 millimeter of the sample when you're doing this. What I've done is I've made a very sharp tip that is a light-emitting source. Now with this sharp tip, I scan it over the sample, sending in characteristic photons. And when I note that those photons have disappeared, I can say that those molecular bonds exist in that location. The great thing about it is that my sharp tip emits from about 1/1,000,000th of a millimeter. So you have a much finer resolution. And the beauty of that is that in doing this, I will have not actually touched the sample. I will have not affected its environment. What I will have done is only made the molecule dance. Thank you.